All right, so this is just some practice with some entropy calculations that we just briefly talked about in class. Wanted to go through it. The solution is also posted, but if you want to hear a little bit of an explanation why everything works, we'll go through it together here in a couple minutes. So let's dive right in. So this first problem, we're looking at water cooling down as it's sitting in a room. Obviously, this is something that happens in real life. So when we run through all our calculations, we should find Sgen is positive, right? We're generating entropy as it's cooling down from 80 down to 60, right? It's sitting in a 20-degree room. That makes sense. Our first step is going to be to find the internal energy change. That is delta capital U. That is the mass times the change in specific internal energy, or mass CV delta T. We can do the math quick. That's 3 kilograms total times our CV, which is 4.2 kilojoules per kilogram Kelvin, times our 20 degree, but that's right, final minus initial, so 60 minus 80 C, and that gives negative 282 kilojoules, not per kilogram, just kilojoules, 252, sorry, 252 kilojoules. If we want to determine the heat removed, we can run to an energy balance, delta U equals Q minus W. The work is zero, the water's just cooling down, there's no volume change. There's no motion that's allowing us to extract that work. So delta U equals Q, so Q, the amount of heat is negative 252 kilojoules, leaving the water. That's why it's cooling down. Right, so we can box that. If we want to determine the entropy change, we need to look at the final and initial state. So delta capital S is mass times little delta S. We can look up on our equation sheet what little delta S is, and that is CV times the natural log of T2 over T1. We have to remind ourselves that using entropy like this, we have to use temperatures in Kelvin. So this is 3 kilograms times 4.2 kilojoules per kilogram Kelvin. That's our heat capacity times the natural log. So we have 80 and 60 as our two temperatures, but translate that into Kelvin. We have 60 plus 273, that's our final temperature, 60 degrees, divided by our initial temperature, 80 plus 273. And that equals negative 0.734 kilojoules per Kelvin. So that right there is our change in entropy of the water. So the water experiences a decrease in entropy. That makes sense, it's cooling down. All right, what we're going to do now is find Sgen. So we'll use this equation that we talked about briefly in class, Q in over T in minus Q out over T out plus Sgen. What we want to do is find Sgen, so this is unknown. Q in, so no heat is going into water from a higher temp. So there's not a heat source where heat's flowing into the water, heat's flowing out of the water. So this we already calculated in part C. That's the change for the water itself. This guy is the heat flowing out. This is part B. And this is our room temp. That is where that heat is actually going out to. So that's our 20-degree room. All right, so let's put this all together. Our delta S, we just calculated that, negative 0.734 kilojoules per Kelvin equals 0. That's our first term because we don't have heat flowing into the system. Minus, and now we have 252 kilojoules of heat divided by our 20 degrees Celsius, or 293 Kelvin, plus S gen. Now the sign is a little bit funny on this. We calculated the sign up here at the top to be a negative 252 kilojoules. I guess down here in D, we could use a sign convention where we also have a negative on Q because heat is leaving. But typically for this, we're just kind of saying what's the magnitude of heat that's leaving the system. So that's why we give 252 kilojoules leaving. All right, if we go through and do the algebra, we can find S gen equals 0.125 kilojoules per Kelvin. That's how much entropy we've generated. What does the value and the sign mean? So the sign, positive S gen, means this, maybe not this occurs, but this is possible. You can't have things that have a positive entropy change that don't actually happen. It's not that they couldn't happen, it's just that it's not happening for whatever reason. This is something that is happening spontaneously, and it's generating entropy, and that positive S gen means that it is truly happening. We could also look, if we wanted to, a little bit at the magnitude. So we did do this in class. Wouldn't necessarily have to do this, but if we want to look at the lost work, this is T, right? D is TDS gen. So we can say that the lost work is 293 Kelvin times 0.125 kilojoules per Kelvin, which would be about 36.7 kilojoules of work. So what that means is we could have gotten 36 kilojoules of work out of the system if we had a Carnot engine and were able to harness our heat perfectly during this process. That's work that we could have gotten, right? We had 252 kilojoules of heat moving. Hey, we could have used some of that. We could have gotten this 36 kilojoules of work. All right, last problem. We have a computer CPU. It's at 60 degrees, right? We have the CPU and, right, it's hot, 60 C. It's getting cooled actively. It's sitting in a room that's 20 degrees C. There's a fan blowing over it. So here's my beautiful fan. Looks sort of like a flower, but that fan is blowing over that, and that's keeping the thing cool. Asked to determine the rate of entropy generation for this process. So entropy generation, we're going to this equation. We have a rate, so we'll do a rate for each of these. This is Q in dot over T in minus Q out over T out plus Sgen, but now this is dot. So we can do this. We can multiply everything by, say, like mass flow rates and be able to scale things just like we've done before. Again, just to walk through this in a little bit of detail, this is the change, really the rate of change for the chip, for our computer chip itself. How is the computer chip itself changing entropy? This would be heat into the chip. So we have electricity flowing into the chip, 25 watts of power, but that's not heat. So it's electricity. Heat and electricity, those are different things. This is specifically talking about heat. It would have to be flowing in from someplace hotter. That would be the T in that you see down here below. That's not happening in this particular case. What's happening is the CPU is being cooled, so heat is flowing out. So this is heat out, and this is the surroundings. Or the place where that heat is ending up out in the room at 20 degrees C. This is our unknown. Right, so setting up the problem is a little bit weird. We have heats and temperatures. You know, you get most of the way there just by finding a heat, putting it over a temperature, and just kind of away you go. But this hopefully helps you organize things a little bit better in your head. Now we can start to fill in these different terms. The first one is the rate of entropy change for the chip. That is 0 because the chip is not changing temperature, right? So we would have like delta S dot equals m dot CV times the natural log T2 over T1, but T2 and T1 are the same, so that's just 0. We don't have heat going into the system, so that's 0. We do have 25 watts of heat going out of the system, and it's going out to 20 degrees C or 293 Kelvin. So what we end up with is Sgen dot, the rate of entropy generation, is 25 watts divided by 293 Kelvin, which is 0.085 watts per Kelvin. Okay, this is again a positive number indicating that this process where heat is being dissipated from the computer chip is a possible process, something that can happen, something that's not reversible. And the quantity of entropy generation, again, gives us kind of this idea of how far from reversible are we. All right, so thanks for sticking along. Hopefully this, again, gives a little bit more concreteness to entropy generation, and how this stuff all fits together. That's the hope, at least. Feel free to shoot me an email with any questions that you have as you're going through this. Otherwise, thanks for watching.